Hello everyone, my name is Dr. Christine Larson and I'm going to be your celestial tour guide over the next 15 weeks as you journey through the universe. I always hear Carl Sagan's voice in my ear when I start talking about grand things like the cosmos. If you all remember that, the original cosmos with billions and billions from Carl Sagan. At any rate, I'd like to introduce you to the wonderful science of astronomy. Astronomy is simply the study of the universe, so technically the study of everything, I guess. But we're going to try to keep it a little bit manageable in terms of the content over the next 15 weeks. So this is week one. Week one is sort of an introduction to astronomy and give you a little bit of historical background. So what I've done is I've written on the board here some of the key points that I want you to keep in the back of your head when you're going through the material in the textbook. One of the really important things that you need to always remember is that astronomy is a science. And science is a very particular way of knowing things about the world around us. So defining what is science is going to be a really good, important place to start in any science course, including astronomy. So you're going to learn a little bit about the scientific method and about the difference between a hypothesis and a theory. Very important because a lot of people use the word theory incorrectly. You're going to see a video of mine where I really go on my hobby horse about that. But just as important as knowing what a science is knowing what's not a science. And an example of that is astrology. So why is astrology not a science? Why is astrology what we call a pseudoscience? So that's going to be a very important distinction that you're going to want to key in very carefully on in the book. Once we know what a science is and what's not a science, how is astronomy different from other sciences? And there are two ways that astronomy is, I believe, very different from the other sciences. The first is we go around with our hands tied behind our backs. I mean, geologists can pick up rocks and they can bang on them and they can do chemical analysis on them and they can scratch them and they can sniff them if they want to. Biologists, they can dissect organisms. They can breed them in the laboratory. Astronomers, we basically look and we don't touch. Remember when your mother told you that? Wasn't that really annoying when you were a little child? Well, imagine you're an astronomer and all throughout your career it's look, but don't touch. A second way that astronomy is very different is that we're always getting old news. Because whenever we look out at something into space, it's taken light from that object some amount of time to reach us. So if I look at the sun right now, I'm not seeing how the sun actually is this moment. I'm seeing how it was 8 minutes ago because it's taken light from the sun 8 minutes to reach me. If I look at Pluto, it's taken that light about 6 hours to reach us. Now, has Pluto really changed in 6 hours? I don't think so. But if I'm looking at the Andromeda Galaxy, I'm looking at what it looked like 2.5 million years ago. Some of the stars in that galaxy have probably exploded by now, yet I'm receiving the light from those stars just today. If you've ever seen the movie Spaceballs, I think you know the very famous sketch that kind of blows your mind like this. But this look back time is a double-edged sword. More about that later on in the course. And then we're going to start with the night sky. And talking about the night sky, you're going to see in the book a two-dimensional representation of this wonderful three-dimensional thing. This is called a star globe. It's more properly called a celestial sphere. It sort of models the old geocentric view of the universe with the Earth at the center and everything orbiting around it. Now, of course, the universe really doesn't look like this. But as you go out into the night sky and you look up, it really does appear as though everything is moving around us. So as long as we just take this as a useful model and don't take it too seriously, the celestial sphere will allow us to have a discussion about constellations and how things look in the night sky. And talking about how things change in the night sky, you're going to be introduced to a concept called the ecliptic. You might know it as the zodiac. And this is very confusing to people because, again, it's a three-dimensional concept and it doesn't really pop out at you on a two-dimensional page. So I did a nice little video that I hope you'll find humorous that I taped in my kitchen. And hopefully that will help explain a little bit more what the ecliptic actually is. And another thing that the Earth does because of its motion is it wobbles. And this is something called precession. And precession, the wobbling of the Earth like a wobbly top, has a very important impact on our view of the heavens over time. You probably have heard of the North Star. The North Star is currently a star called Polaris. But the ancient Egyptians viewed a different North Star because the Earth has shifted. It's wobbled since the time of the ancient Egyptians. So there's a web page that will help you understand more about precession. And after talking about ancient astronomy, the book then goes on and talks about the very important Copernican revolution, how we figured out that, sorry folks, we're not the center of the universe. Okay? There actually is no center of the universe. More on that week 14, 15. Okay? But the Copernican revolution happened in steps. It didn't happen like somebody didn't wake up one morning and go, Eureka, I figured it all out. And there were parts of the Copernican revolution that were steps in the right direction. And there were parts of the Copernican revolution where they just couldn't give up on ideas that were wrong because of personal bias. That's right, scientists can sometimes have personal bias that affects their science. So when you read about the Copernican revolution, think about what it would have been like to be in Europe in the 14, 15, even 1600s. And think about how difficult it was to give up some of those long-held preconceptions. And part of the actual Copernican revolution was using our observations of the night sky, largely done before the telescope, and using what the universe was telling us to come up with a correct model. So there were going to be a number of different observations that were done by people like Tycho Brahe, which were very important in figuring out the actual motions of the heavenly bodies. And one of those observations deals with something called retrograde motion. Retrograde means backwards. And retrograde motion, in this case, this means an apparent backward motion of the planets. It's not true that the planets sometimes move backwards, but as we view them in the sky moving through the constellations from week to week, they occasionally will do a funny little wiggly dance, and that's the retrograde motion. If you think about it, if you're on the highway and you pass somebody out who's going really slow, and you look at them in your rear view mirror, doesn't it look like they're going backwards relative to you? Now, we hope they're really not going backwards, because that would be very bad. But it looks like they're going backwards because you're going faster. Well, the same thing is going to be happening here. You're going to learn that the faster moving Earth passes out a slower moving planet like Mars, and this is going to make Mars appear to go backwards as viewed relative to the stars at certain points in our orbit and its orbit. So those are just a few of the points to keep in mind as you go through the material for this chapter, actually 2 chapters, and I look forward to answering any questions that you might have.